he said, tell us about what you're researching right now. And I haven't really given a talk on what I'm researching now to a general audience before, giving presentations to lots of engineers. That's kind of, and so I kind of got nervous about this, thinking, how do I give a presentation about this topic? I'm used to giving topics that I think are kind of intuitively interesting to people. When I first, before I left Central Washington University and came to the Nuclear Regulatory Commission, I was working on a great topic. Spotted owl, Pacific Northwest, endangered species, major political fight in the last couple of decades of the 20th century. And it was going to be a really interesting topic. I was going to have a lot of fun with this. I was going to go to logging camps because it had two kind of questions. You were dealing with an endangered species, and it was also, we're talking about a story that had a major economic impact in the Pacific Northwest. It's going to be fun. Oh, by the way, that owl was as close as it looks in that photo. They do exactly what I've always heard. They come fly right down, bam. They defend their territory. They stand, right on a branch next to you. That was my topic. Then I go to the Nuclear Regulatory Commission, and I go from studying a charismatic MIDI fauna to engineers. I always try to find a way to get this photo into my presentations. This is a guy named Steve Hanauer. I have a building full of people who look like this without the sideburns. Yeah. Steve had, there's two words that always described him, brilliant and narcolepsy. And I'll save that story for later if you want to ask about it. But this is what I have to study. Is I have to study engineers who write reports with covers that look like this. And that cover is the most exciting thing in the report. I have pages that I have to look at that look like this, and this, and this, and this. But this is important. How we understand risk today largely comes out of this report, the Reactor Safety Study published in 1975. And I don't mean risk the way we traditionally think of it, the things we know. Just do one quick thing. Risk, the probability of something happening and the consequences. Put them together and you have an expression of risk. And consequences, probability. The problem was always probability. What's the probability of a major reactor accident? But how we understand risk now is really largely, it comes from this report. And I'm talking about in a host of areas. It's not in the areas you traditionally think of. Risk, flying an airplane, driving a car. You bring in actuaries, they total up the number of accidents, they figure out how far people drive, and bam, they hand you a premium, right? And you pay it. We understand that kind of risk. But out on the far edges of risk are two things. There's low-level chronic exposures to hazardous substances that we can't really estimate. And at the other end, catastrophic risk about events that hardly ever happen. How do we understand risk today? That largely is a result. The work that we have done, scientists, engineers, in trying to understand the risks from radiation have largely affected what we think about that today in a host of areas. When you pick up an apple and you go over the sink and you wash it, that's largely because of how we understood risk when it comes to radiation and reactor safety. Now, we had a little bit of data about how people understood risk or were subject to risk of radiation going back to the early 20th century. You've heard of the radium girls, no doubt, the women who were exposed to radium by licking the brushes and painting watch dials and getting cancer from it. There was also plenty of examples of consumer products that people could buy that had radium in it and that were supposed to be healthful. This is a water jug, put water in it, exposed to radium, and it was supposed to help you. This is Radithor, that was also a radium bottle. People would drink that straight up as a healthful product. And these, I have to get into any presentation, are condoms laced with radium. So there was plenty of examples where people used radium in strange ways, and there was some health data on it. But we didn't really understand radiation and its effects at the very low end of the scale. How do you measure that kind of risk? Now, keep in mind, we didn't initially, after World War II, understand risk from radiation because of a bomb. It wasn't quite clear, because that was a major, blast of radiation that people got in a very quick period of time and some fallout afterwards. And really, right after World War II, radiation was still seen as this potential health boom, as this image from Collier's magazine kind of implied, that it would provide cures for things like paralysis and the like. So there was always hope. How we started changing what we thought about radiation came really from the work of a guy named Herman Muller, who had done work, eventually won a Nobel Prize, but he had done work on the effects of radiation on fruit flies and discovered that chromosome damage, you could have genetic effects. And so after that point, in the late 1940s, we started really looking at risk at low levels in a different way, that even small amounts of radiation could do damage. And with the advent of atmospheric weapons testing in the 1950s in the United States, people began asking, what is the chances that you could have major effects on the human populations all around the world from weapons testing, and low levels that just would come down and fall out and wind up in rivers? I love this magazine cover. Groups that were opposed to the bomb also started to imply that small amounts could do real damage. This is an advertisement that came out in the early 1960s when they were still campaigning against above-ground atmospheric weapons testing. And as you know here, children having strontium-90 in their teeth. There was a whole campaign to collect teeth, bring them in, and they would measure the strontium-90, and they put these advertisements out. So by the early 1960s, the public's recognition, growing recognition that there were hazards all around them, small, low-level hazards. And as this Bill Maudlin cartoon shows, radioactive fallout, this family very carefully holding their lead umbrella above them to keep the radiation off them. There's a growing recognition that low-level radiation could do damage. And that really started shifting attitudes about the safety of radiation, or the hazards of radiation. Now, how did we understand risk before this? Well, if you look at this, this is what they call a linear no-threshold model. I'll explain. What they used to think in the 1940s and earlier is that damage, health risk, radiation dose, ran down to some point down around where background level radiation that you're always exposed to, which is about 200 millirem a year. Once you got down to that level, they figured, they assumed there really wasn't significant damage. There was no visible damage. There's no studies that showed anything less than that was a danger. But what happens in the late 1950s and early 60s is they revise the model. They basically assume, they don't have any proof down here, but they basically assume as you get down into very low levels, it's linear, all the way down. Get struck by one ray of radiation, damage. Two, more. All the way up. And so that changed the dynamic. Every little bit of exposure, it was assumed, regulators had to assume, would do damage. So if this is the assumption, it means that there's a probability of damage no matter how far down you go. There's no safe level. And so if that's the case, then any operation of a nuclear reactor presented some level of risk, right? So how did we make sure that reactors were safe? There'd never been a reactor accident. So they went off and they tried to create accidents like this one in Idaho. You could have an explosive release of radiation from a reactor, not like an atomic bomb, but more like a chemical explosion as we saw at Chernobyl. So how do you prevent this? How do you prevent this problem? Well, what they did initially, when they made the plutonium that went into the bombs in Nagasaki and New Mexico, they put the reactors that made the plutonium out in the middle of nowhere, eastern Washington, where Jim and I used to live. Sagebrush and rattlesnakes. Miles around, nothing. So if something went wrong at one of those reactors, safe, simply because of isolation. Now the problem with this is that if you're going to build nuclear power plants, they can't be in the middle of nowhere. They have to be near cities, right, where that's where people use the electricity. And utility companies were very interested in having reactors very close to people. That's where Con Ed wanted to build a nuclear power plant. United Nations building, Chrysler building, Empire State Building. Now, needless to say, the Atomic Energy Commission did not approve this. They couldn't believe Con Ed wanted to build this. They just really couldn't believe it. But anyway, they had to go through the process of saying no. Well, if you're going to put a power plant that close to people, how do you get to safety? Well, you kind of know the answer is, well, okay, you put a real sturdy containment building around the reactor. Zero, right? All power plants in the United States have some version of this, a containment building, big steel, concrete structure that's supposed to be able to take high pressures, high temperatures. Some of them are built to withstand airplane impacts and the like. Okay? So that's how we got to safety. Now, they don't know probabilities of an accident at all. There's no accidents. You have no history. All you can do is say, this looks good enough, to simplify too much. But there's a problem. They finally discovered in the mid-1960s, in the middle of the 1960s, well, there's a problem with this, putting it in a concrete building. Here's a reactor. Water keeps it cool, circulates through this piping. Pipe breaks, they say. What if that big pipe breaks? Water all comes out? Well, the fuel continues to keep putting out heat. Eventually, it puts out so much heat that it starts to melt, lands on the floor of the containment building, and because it's 5,000 degrees, it eats through the bottom of the containment building. And then, what do you have? A movie. Okay. The China syndrome was a real thing. It was not just something that was made in a movie. It created a major crisis among regulators, reactor safety regulators back in the 1960s. Because the problem was this: if that containment building will not hold, then you don't have a kind of absolute guarantee of safety. And so what the Atomic Energy Commission that regulated the safety of reactors had to say was, well, yes, this might happen, but the probability of an accident was really low. And people would say, well, how low is it? And, well, it's really low. Yeah, but how much? And we don't know. We can't answer that. There's never been an accident. How do we do this? And pressure grows through the late 1960s and early 1970s to do something. Say, how safe are these reactors? There's a growing anti-nuclear movement by the late 1960s, early 1970s. Henry Kendall, MIT physics professor, Nobel Prize winner, founds the Union of Concerned Scientists and leads a charge against nuclear power plants, argues that they're not safe enough, that they haven't done the research. And the Union of Concerned Scientists, I mean, he's a Nobel Prize winner. I mean, these were well-informed people that were questioning the safety of nuclear power. People in Congress said, well, can't you guys show us how safe reactors are? And so there's growing pressure to quantify the safety of nuclear power plants. And they need to do it because they have to kind of reassure themselves, these regulators, that nuclear power is safe enough. Now, how do you do that? Okay, don't look too carefully at this. I won't quiz you on it later. A guy named Chauncey Starr says, okay, I got an idea. I'm going to develop a numerical basis so we can compare every kind of risk that's out there. Whether you're riding a bicycle or operating a nuclear power plant, we're going to be able to plug this into this formula and out pops a number, and we're going to say the public will accept that. Now, he understood. What he did is he went back and he looked at and he tried to figure out there must be some kind of formula in people's heads about what is safe enough. If it was a voluntary risk, he said, oh, people are willing to take on voluntary risks. You'll climb a ladder to clean out the gutters in your house, right? But even despite the fact that that's much more dangerous than doing lots of other things that you wouldn't do. So voluntary risks, people were willing to take on risks that are 1,000 times more likely than involuntary risks like nuclear power. He plugged this all in, and bam, he came up with a formula that said nuclear power and other electric sources are safe enough. And so we're going to put everything, and we're going to have a number for all risk. And this article was amazingly influential, not because it was so good, but lots of psychologists and political scientists went off and studied it just to prove how wrong it was. Okay. Because what Sean, I look at this and I look at what he did, and I find it kind of charming, because he really believed if we just put numbers in front of the public and we show them that it's very, very unlikely that a reactor will melt down, that they'll be convinced. He had this kind of, enlightenment view that if we just put the evidence in front of people and give them a number, they will be happy with that. And they'll trust us, and we'll go off and build lots of nuclear power plants. And it's important to remember why he believed that in 1969 when he wrote this article. There was all kinds of studies that are going to come out in the 1970s and the 1980s, done by people in psychology in particular. And they're going to study how people really evaluate risk. The two best-known people are Amos Tversky and Daniel Kahneman. Daniel Kahneman eventually wins the Nobel Prize in economics for these studies. And they come to the conclusion, they and a lot of other scholars come to a conclusion, that the public really has no clue about risk, that they really don't understand how to evaluate risk. There's no logic to how they evaluate risk. There's all kinds of biases. Experts have biases too, and I'll get to that in a second. But the public, really, there is no logic. There's no formula like this. But this is going to take a while for people to figure out. In the meantime, this idea seemed like a great idea. All we got to do is quantify risk and show it to everybody, and as long as it's really, really unlikely, it'll work. And basically, lots of government agencies go off and they start developing goals, numerical goals, about how unlikely the risks were that they dealt with. The Atomic Energy Commission, basically 1 in a million. That's what they said. We think a nuclear power plant, the odds of an accident are about 1 in a million. The EPA, they also developed a standard, 1 in a million. FDA, same. Supreme Court, when they expressed an opinion on this in the early 1980s, the mid-range was 1 in a million. NASA, they were the pessimists. A space shuttle launch, 1 in 100,000. I'll come back to that. Okay. So this is the idea. If as long as you were in the range of about 1 in a million, that would be good. So all the Nuclear Regulatory Commission and the Atomic Energy Commission, the AEC breaks up and the NRC takes over. All they had to do was develop a study that showed what were the real odds of a nuclear reactor accident. And so they came up with one, and it's a very complex, and that was what those pages were that I showed you, way to estimate the risk of an accident that had never occurred yet. And so they came up with, the key thing was, they came up with results like this. And if you look at this, you can see up at the top, oops, wrong one. Up at the top, you can see natural events, tornadoes, hurricanes, earthquakes. Frequency of event, much higher than a nuclear reactor accident down here. And the fatalities associated with that would be much higher as well. Down here, nuclear power plants were down in the same category as getting struck by a meteor. Right? So the message was clear. Unless you're laying in bed at night worrying about, one coming out of the sky and hitting you, you don't need to worry about nuclear reactor accidents. So that was the key message. But this study did a lot of other things that really changed how we think about things. One thing they did point out is actually no, a reactor accident is much more likely than 1 in a million. About 1 in 10,000 they came up with. But they said the consequences of that accident were much lower. So they basically increased the frequency of a reactor accident from 1 in a million to 1 in 10,000, 100 times. That was significant. All of a sudden, you start getting into the range of something more realistic. So some of the key insights: accidents more likely, consequences less. And they concluded, as you saw by that graph, that risk was negligible for nuclear power plants. But they also pointed out something else. there were a lot of different ways that you get to an accident. Human error, maintenance problems, things break. And then there's a chain of events that can lead to a major problem. So those were all major insights. But the one problem they did not really do well, and this got this study a ton of criticism, was that there were huge error bands in their estimates, very, very large. And so they got raked over the coals by that. And the Nuclear Regulatory Commission eventually said, you know that graph, forget it. It doesn't work. Pretend like we never put it out. That was in 1979, January. They kind of retracted that part of the story. But what eventually, let me skip over that. What eventually changed things was 3 Mile Island. 3 Mile Island was an accident that was tailor-made for that report. 3 Mile Island happened in 79. The report came out in 75. 3 Mile Island occurred because of human error, maintenance problems, things broke, a series of events, a lot of happenstance that comes together to lead to a major accident. And all of a sudden, this report starts to look a lot better. And in the 1980s, there's a series of events that seem to confirm the basic insights of this report. Bhopal, operator error, design problems, maintenance issues, and basically operators who had no idea how dangerous what they were dealing with, what really was. Quantifying risk mattered. And of course, Chernobyl. Operators there had no understanding of how likely it was for an accident, no understanding of what could happen, and of course, a lot of other design problems. These kinds of risk assessments really could make a difference. Space shuttle. Not operator error, but NASA, remember I said 1 in 100,000 launch? For that number to be correct, they would have had to have launched a shuttle every day for 350 years or something before they would get one accident. Because they did not attempt to quantify risk, they badly misunderstood what the risk was that day. Now, you probably know a little bit, you might remember a little bit of the story of why the Challenger fell apart basically in midair. It was largely a cold day. You can see that in the photo. Those people all have coats on in Florida, right? It was below freezing. O-rings, little rubber O-rings that kept seals around the solid rocket boosters. If in the cold, once they got compressed, they didn't spring back. And so there's a gap, gas rushes out, and the Challenger comes apart because of the hot gas that's escaping. Nobody understood just how likely that accident was, except risk assessors who had done this work on the study that I told you about. Nuclear experts had pointed out that the chances of a shuttle disaster were somewhere between 1 in 50 and 1 in 100. And they were arguing with NASA, not about the launch specifically, but in a general way, that the risks to the shuttle were much higher than anybody had really estimated before this. So the problem was that people simply did not, by not analyzing risk, a lot of the big embarrassments, the big disasters of the 1980s occurred. And the shuttle had a kind of big moment. There was a big hearing. A guy named Richard Feynman, Nobel Prize-winning physicist from Caltech. He was quite a grandstander, and he kind of demonstrated all this in a kind of famous moment where he took some of the O-ring, puts it in a clamp after putting it in ice water, clamps it down and shows that it doesn't spring back. And he blamed that accident on management, NASA management, because he said that there was a can-do attitude at NASA. They were going to launch it, at any cost, and that they were lax. But I think it's something different. What you see across all of those estimates I showed you earlier is that people, and this is what a lot of this psychological research showed, experts were routinely overly optimistic about the odds of disaster. And they were also very confident, too confident, in the precision of their estimates. And the reason they did this is because they had no evidence. They had no probabilities to defend their points against. And so largely, the people who went into these disasters did not understand the risks that they faced. Fukushima. Of course, Japan, probably better than any other country, understood not only earthquake risk, but also tsunami risk. But they thought it was isolated to the Sanriku coast right up here. How many of you have ever heard of the Onagawa nuclear power plant? One, okay. Most of you don't remember it because nothing happened there. Because it was built in the tsunami coast, where they thought that they always had tsunamis, they built a 14.8 meter high wall. And no one remembers Onagawa today. The tsunami, when it came in, was 13 meters high. Just enough. Japan did not understand the risk of tsunamis down here. Along this coast, they thought that they didn't have tsunamis. And so Fukushima, and how did they believe this? Japan had a long history, a long written record of all of the major quakes in Japan. They had designed all their seismic safety around it, and they had no record of tsunamis on that stretch of the coast. And so they didn't build a wall. And so, you know, there's areas of risk out there that surprise us. In trying to estimate probabilities, there's always some unknown out there. The unknown unknowns is, you know, of course, was famously mentioned. And so Fukushima wound up having an accident that no one had really thought was quite possible, at least not until a few years before then, when they actually started discovering evidence of tsunamis back in the past. So Fukushima made us rethink how we approach risk and probabilities of risk going forward in nuclear power. And one of the key recognitions that you have is that there are accidents that you're never going to imagine. Not only at nuclear power plants, but refineries, like we saw at Bhopal and the space shuttle. How do you prevent against them? And so what the NRC has moved toward in recent years is a greater emphasis on allowing operators to adapt in the moment, what they call mitigation, developing emergency equipment, which was not present at Fukushima, so that they can adapt and deal with risk. So that I'm trying to give you a kind of broad sweep of how efforts to understand risk have influenced how we deal with risk today. Oh, by the way, I just wanted to show you this photo just to give you an idea of what the tsunami was like at Fukushima. This is the top of one of the reactor buildings. That's about 150 feet, 160 feet above sea level. Here's the wave. So that's 200 feet. Yeah. Now, when a tsunami wave comes in, it's more like the whole ocean just rises up and stays up at a high level for like 20, 30 minutes. You know, it's not exactly a wave like a surfing wave, even though you kind of get that effect there. What really got the reactor was just the fact that the water stayed up so high for so long and ultimately disabled all of the emergency equipment. So one of the answers is whatever the unexpected is, you have to have emergency equipment for dealing with it. So a lot of the assessments that have been done, probabilistic assessments, to look at these kinds of accident probabilities is really focused on trying to understand how you can adapt in emergency situations. And so that's a part that was really not out there in the 1960s. You basically came up with a design, and the emergency procedures really weren't covered as well. Okay, so just a kind of closing assessment here. Risk assessment. It has wide application. I haven't really talked about it, but risk assessment, this kind of probabilistic risk assessment, looking at probabilities and consequences, it's done in a ton of areas now. Not only nuclear power, but as I said, oil refineries. They even do it in looking at terrorism. They use the kinds of assessment tools that the Nuclear Regulatory Commission developed back in the 1970s. But one thing it really did not do, what Chauncey Starr hoped it would do, is it would persuade, it would convince the public. That never really happened, because ultimately, what you believe about risk is based on who you trust, what kinds of people you put your faith in. And if you don't trust the experts and the scientists, then you're not going to accept the evidence they present. People are more affected by events and what they know. There's a lot of dread of certain kinds of technology risks, other kinds of health hazards. That's what usually affects people. So risk assessment's been more, I think, of a success for engineers and designing safety than what its original goal was, which was to persuade the public. And today, policy decisions are really kind of a mix. It kind of recognizes that the public isn't going to accept just a number, straight out number. So it's going to be a mix of kind of qualitative factors, what the public will accept, as well as looking at what these probabilities purport to show. So that's the project I'm working on. So the good part is I get to talk about disasters. People love reading about disasters, right? So that's the one good part of it, even though I also am in a building with engineers who look like Steve Hanauer. So, okay, questions? And then, okay.
So would you say, sorry. Yeah. So would you say when those kind of emergencies happen, that's mostly what informs risk management plans, or have there been instances of pretty effective risk management plans in place ahead of emergencies like that?
Well, after it's emergency. I actually the previous lecture I gave, I showed the first emergency plan for a nuclear reactor. It was a college university reactor. It was one page. And it had 4 bullets on it, and one was call the police. It had a secret code for what was going to go wrong. And somehow the secret code was an emergency nuclear reactor. That's not a code, And so emergency response has been developing slowly. By the 1960s, 1970s, you'd gotten to the point where the paper response plans were pretty good on paper. After 3 Mile Island, you get much more effort at developing practical response plans, practicing. And then probably before you get to Fukushima, the other kind of key moment is 9/11. And that led to a massive improvement in developing emergency response plans across multiple agencies. And the NRC, really massively increased its efforts at emergency response and developed regulations that kind of started down the path of requiring utilities to have emergency equipment, the kind of things that could have made a difference in a case like Fukushima. So I think what's interesting is they always thought that these kinds of emergency response efforts were important, but it took time to develop it. It's over a period of over 50 years. So it's kind of an evolutionary process. I can't think of one moment. Is that, okay.
Not so much a question, but a point of reference. You referred to the Challenger disaster and blame NASA management, which surely that's where the blame was. But there was a lot of pressure on them to get that launch going because it was the first time we had a citizen, a teacher, going up in space, and there was a lot of media attention to that.
And their budgets were getting constrained, and so they were under pressure to show that they could make money. These launches were supposed to pay for themselves. So NASA is. You're right. They're putting the first non-astronaut in space, right? But they were also under pressure to show that they could make a budget. That was how the space shuttle was sold, right? It was going to make money. They were going to be basically a ferry service into space. So there was a number of pressures on them to launch. But I mean, if you look at some of that decision has been studied endlessly. Sarah Vaughan was a person who put out just a massive book on it. It's really fascinating to look at the way that decision unfolded. And there's some people who argue that there was this group of dissidents in Morton Thiokol, the manufacturer of the booster, and say, oh, we shouldn't launch, and you don't really find that evidence. There was, kind of some squeamishness, but nobody really understood what the risk would be that day. So there was, you're right, there was pressure. There was pressure to get the launch off, but the dangers were not. Nobody basically said, can't do it. It's too dangerous. It was a much more kind of muddled decision than that.
Yeah, so I've studied that Challenger launch fiasco as well, and exactly as you were saying, NASA had claimed before that the odds of a catastrophic shuttle incident were 1 in 100,000, and then after that 25th launch of the space shuttle, they had to recompute the odds to be 1 in 25, but then they went ahead and said, well, we're going to go and make it really safe right now, be completely realistic, and after all that, they said, well, now the odds, we're ready to launch again, and the odds are much more realistic at 1 in 1,000. And then they have the 113th launch of the space shuttle, and that's Columbia, so then you got to go back and historically recalculate that to be 2 in 113. Oh, right.
Yeah, re-entry. Yeah.
But then
the total risk of the loss of vehicle during the whole mission. Yeah.
And then also you were mentioning about the Onagawa, and wasn't the sort of architect or designer of that nuclear power plant, he was very insistent and almost to the point of, if you don't do it, I'm going to quit?
Yeah, there was a safety committee that actually had a long-running debate about building that wall. But if you look at the other power plants up and down the coast, because they were located where they were very aware of the tsunami risk. The other plants up and down the coast didn't have that same discussion because they didn't think that it was a major risk. Yes, there was, because of where they were located, that kind of launches the discussion, and they eventually, build a full-scale wall that the others didn't. But it's one of the arguments that the utility TEPCO that built Fukushima argues is that nobody built, other than Onagawa, nobody else built a wall like that. It was a kind of unique situation because they were so aware of the risk.
I read that's also a very good example of regulatory capture, where basically the industry that supposedly a government agency is set up to regulate gets people from that industry running it, kind of like the FCC and the EPA right now. And so it's like the fox watching the hen house.
Well, that was a criticism of the Japanese nuclear regulatory process in general. I've looked a lot at that, about how that decision to build Fukushima was originally done, and I don't know if it was regulatory capture. It wasn't like you can't find some regulator back in that day saying, you guys ought to build a wall, but then caving to it. Yes, the Japanese regulatory system, has since changed and become much more independent, but at the time, they did have a kind of reputation for being too closely aligned with the industry. That you can find mentioned often. Yeah.
Really cool talk, thank you. So you said that the image, based on like the estimate, that the tsunami was 200 feet high?
Let me go, oh, rats.
And I know that's a very rough estimate based on like visual estimation.
If you look at, you can see that the water basically goes straight up. But if you actually look at how high the water level came up, it actually kind of just flows in. The water is kind of like hitting a bunch of buildings and going straight up. But the water level that actually comes up and floods the area was it was about between 45 and 48 feet above sea level. So the actual part that comes in and floods is lower than that wave. But that's when it first strikes. But it gives you an idea. If you look at this area here, these are buildings that are 3 stories high. So that's a lot of energy. But the part that actually does damage is just the water that just kind of flows in, just like a river, and fills up the buildings. It wasn't the force of the wave; it was the fact that it flooded so many levels.
Okay. So in this case, that 14.3 meter wall might actually have helped, despite the fact that the wall
likely would
60
have.
meters high.
Yeah, it likely would have, because at this point it was 13 meters. I think it was. So if they had built a 14-meter wall, it would have made a difference.
You can hear in the media reference to different scenarios as far as accidents to happen. So can we assume that most of these scenarios in which they tell us that to die in an airplane crash is, 1 in 2 million, whatever, that they basically haven't reviewed these scenarios to the same extent, and we are being
well, keep in mind,
something that is not quite right.
But you're talking about airplane accidents.
Or any of the, the accidents that they tell.
Well, I mean, it's just an airplane accident, an automobile accident, getting struck by lightning. There's lots of data on that. So it kind of falls in a different category. We understand the risk of an airplane accident because we've had a fair number of airplane accidents, and they had, a kind of grisly, a number early on, and insurance companies said, well, we're not going to insure you unless you improve safety. So we have a kind of, for those kinds of accidents, these accidents that are frequent, we have a good database and we have a good understanding. It's infrequent things that are much harder to wrap your arms around and come up with an estimate. One of the problems that, they'll tell you that one of the most difficult things to estimate is what is the real risk of sabotage. They've been trying to estimate the risk of sabotage going back to the 1940s, and it's very difficult to kind of come up with a model that really gives you a good idea. So it's the things that hardly ever happen. That was what these engineers are trying to wrap their arms around, is how do you do this when you have no accidents to use? But now since we have 3 Mile Island, you have Fukushima, you actually could say you've got something. It's still a pretty, 4 reactors is still a pretty small number to go to the bank on. But but when they were first developing this, they had nothing, no accidents that were significant. There was a couple small ones at test reactors, but that's it.
So how, thank you for the talk, it was really fascinating. So how does the occurrence of these rare accidents, even though the risk is still very small, how does that change perceptions by the public, acceptability?
Well, one of the biases that affects anyone is they rely on the most dramatic things that they can imagine, and so it tends, if you ask someone to compare the risks and benefits of nuclear power to, say, a coal or an oil plant, it's the catastrophic potential that most dominates their thinking, and they will tell you that the risk of a nuclear reactor accident is much higher than it really is. I mean, it affects your bias so much that you can't even get people to agree that the benefits of a 1,000 megawatt nuclear power plant are basically the same as a 1,000 megawatt coal plant, even though that's kind of obviously true. So there's a lot of biases that go into both the public's and expert estimates when they're looking at risk. Experts are better at it, but they still have their issues too. So yeah, it's these kinds of you don't think through something logically. You pull to mind what they call anchor bias, for example. You've probably heard of that term. There's a number of factors about the way you process, the order you actually get information that kind of bias you toward or away from a risk.
So I'm going back to, whenever there's an airplane accident, the FDA recommends to all the airlines to do all these new, establish new regulations or new something to prevent that particular accident to happen again. With the risk assessments on reactors, so that goes back to all the reactors that have been constructed, since the 1960s, 1970s, and do changes on those based on the new evaluations they have done?
Oh yeah, I mean, and one of the areas that really did not get a lot of attention in the 60s and 70s was maintenance, and so the NRC put in place requirements for greater attention to maintenance on safety systems. And since those regulations have been put in place, 3 Mile Island occurred because the reactor just shut down, right? There was an equipment malfunction and the reactor shut down just like it was supposed to. And then everything went wrong and there were indicators. So one of the lessons was, if you don't have these accidental shutdowns because of bad maintenance, you have a safer plant. And so plant operational performance is, for those kinds of accidents has improved dramatically. It used to be, once now a reactor starts up and operates, it won't shut down for a year and a half. And they rarely have these accidental shutdowns anymore. They used to have them several times a year. There's ways that you can improve safety that are not these kind of big dramatic moments like Fukushima that dramatically improve safety. So, so there's been a lot of regulatory upgrading in ways that people don't think about. That's kind of obscure. I mean, who thinks about maintenance? Well, I do, because actually I wrote about it in the book I'm developing, and God, I hope somebody finds it interesting. So, Jim.
I'll throw out two questions with the understanding that there's really only time to answer one, so you choose. First of all, at the very beginning, you defined risk as, I think, probability times consequences. So my first question would be, since you focus so much on probability, maybe you could say a few words about consequences. What is the worst thing that can happen? And the second question, since you mentioned insurance, is to what extent does the NRC work with people or data from the major reinsurance agencies, Munich Reinsurance, Swiss Reinsurance, that sort of insure the insurance companies of the world in case of some regional disaster? Do you work with these folks at all?
Oh yeah, there's a lot of, as a historian, I don't get involved in, but the nuclear insurers, I'll answer that first, the first part, the second part first, is a major factor. But one of the problems they always had in working with nuclear insurers is they want, they're used to, as I said earlier, they want data. They need, and so this methodology that was developed, the insurers always kind of looked at it funny for quite a while. I mean, as things have improved in the operations, they obviously see benefit, and they want utilities to do more of it. But yes, they're used to basically counting up the bodies and coming up with a conclusion about automobile accidents. That's what they're used to. So this has been. They've been working with insurance companies since the 1950s, quite intensely. But it's one of the reasons why they have that additional insurance. The federal government provides additional guarantees in case of a major accident, because the insurance companies really didn't feel comfortable estimating what the true risk was. Consequences. This is, as I mentioned, they kind of discovered that accidents were more likely, but consequences less. The original estimates, they just kind of sat down with a piece of paper and they say, okay, if you take basically all the radiation inside of a containment building during an accident, we're going to eject half of it out of the building. This is what we think will happen. This is how many tens of thousands of people will die. And as time has gone on, they realize that that's been a kind of massive overestimate in what the actual consequences are. Which is why that you see that even in a case of Chernobyl, where basically the reactor heaved its guts out and tossed it across the lawn, the number of people who died after Chernobyl, the estimates, there were some estimates that it was going to be in the tens of thousands. And at this point, it doesn't seem like we're above 100. So the consequences have been less, even though the mishaps were greater than initially expected. So that's, yeah, so consequences actually, they always felt like, if anything, they were being too conservative with the consequences. So they always felt like they had it in hand, they were using the linear model, which even whether that is correct or not, it was conservative, it was safe. So if you were using it, it was safe. It wouldn't be worse than that. So consequences, actually, there's always been less concern about it than the probabilities, just because, if anything, they knew they were overestimating. Sure.
Yeah, so just to ask the perennial question of how does climate change affect this? Has there been really concerted effort in the risk assessment field to retool our statistics for environmental factors that are no longer accurate?
For what the Nuclear Regulatory Commission does, no. I mean, there's all kinds, of course, like UN bodies, are looking at risk estimates for greenhouse effects all the time. The Nuclear Regulatory Commission, though, I mean, they're very focused on what happens inside the gates of the people they license, inside those power plants. And the utilities just want to know, okay, what's the chances I'm going to get to a core reactor damaging accident? And so the NRC has to focus on that, its licensees. So it doesn't get, the big questions are not going to factor into how they do those estimates. That's, other people use similar ways of estimating risk in those areas. They've taken inspiration from it, but it's not something we do. NASA, I should point, NASA is something that's more directly relevant to what the NRC does, and the NRC has been very influential in getting NASA to adopt a lot of these risk estimate programs and approaches that the NRC originally used. So that's, you can imagine that that's a more directly relevant application of what they did. So NASA now uses this kind of risk assessment all the time. Okay. Thank you.
And also, if I can ask you a favor, and if you could take one chair to the back, that would help us really a lot. Thanks. Thank you so much. It's a little token from the